We see the headlines all of the time. Scientists have successfully achieved teleportation. It sounds like we're finally about to leave our morning commutes behind. But what's actually moving here isn't matter, it's information. You have to completely throw out the classic sci-fi idea of beaming a person from a ship to a planet's surface. In classical computing, your phone or laptop communicates by endlessly copying data, strings of ones and zeros duplicated over and over. Quantum computing works entirely differently. It relies on transferring a highly complex, fragile condition called a quantum state. Because these quantum states are impossible to copy, they happen to be the foundation for a communication network that is physically unhackable. There is, however, a massive roadblock standing in the way of building that network, a rule called the no-cloning theorem. This is a hard law of physics. It states that you simply cannot create an identical copy of an unknown quantum state. If you try to run it through a standard duplication process, the system fails. Any attempt to even measure or read that quantum state violently shatters the original information. You can't observe it without destroying it. This creates a fascinating paradox. If the universe physically prevents us from copying this information, how can researchers possibly send a quantum state across the world without breaking the laws of physics? Physicists found a loophole. They developed a precise routine, often called the Alice and Bob protocol, which acts like an elaborate heist to bypass the cloning restriction through destruction. The setup works like this. Two parties, let's call them Alice and Bob, each take one half of an entangled pair of particles. They can be miles apart, but their particles remain permanently linked by an invisible tether. Measuring one instantly affects the other. This is our inside man. Next comes the target. A third particle containing a mystery quantum state appears on Alice's end. This is the exact information she needs to get to Bob. To execute the transfer, Alice forces her two particles to interact, and then she measures them. The moment she does this, both of her particles collapse into dust. The quantum state is left in limbo. Alice's original mystery state is completely erased in this process. She no longer has the information. That erasure is the entire point. Because the original state is gone, no duplication happened, keeping this operation strictly legal under the laws of quantum mechanics. Even with the particles entangled, the heist isn't finished. Bob's particle has changed, but he doesn't know how to reconstruct the mystery state until Alice tells him the results of her destructive measurement. This message cannot travel instantly. It has to obey the universe's absolute speed limit, the speed of light. So Alice sends a standard classical message to Bob, a simple 2-bit packet traveling over a regular wire, carrying the instructions generated by her measurement. When Bob receives those 2 classical bits, he performs a specific operation to adjust his entangled particle. Instantly, Bob's particle morphs into a perfect replica of the mystery state Alice had at the very beginning. The state successfully transferred. Nothing physically crossed the space between them, the original wasn't copied, and no information moved faster than light. This exact process isn't restricted to theoretical thought experiments on a chalkboard. It is actively running through the infrastructure right beneath our feet. Researchers have now managed to teleport quantum information across long distances using existing commercial internet cables. While millions of particles of light stream through these fibers to carry conventional web traffic, single photons carrying quantum states weave right alongside them in total harmony. Scientists successfully teleported this data across miles of an actively busy network, and it didn't disrupt a single byte of normal internet traffic. Demonstrating this in a real-world environment proves that we can build a highly secure quantum internet directly on top of our existing telecommunications grid. The mechanics of this protocol carry heavy implications. We are essentially disassembling the mathematical profile of a particle in one location and rebuilding it on the other side of the planet. In our standard digital lives, data is infinitely reproducible. But in the quantum realm, there are no backup copies, there are no duplicates. There is only one precise, transferred truth. Imagine a global communication network where your data privacy isn't protected by a password that could be cracked, but by the physical laws of the universe itself. If an eavesdropper even looks at the data, it destroys the information and alerts the sender. This protocol provides a physical bedrock for how we will store, transmit, and protect information in the decades to come.